What's up guys, this is LeetCode 102 binary tree level order traversal. Given a binary tree, return the level order traversal of its nodes values, for example from left to right, level by level. For example, given this binary tree here, we have this result. So the result is a list of lists, which each list has the nodes in the current level, the nodes in the levels of this tree. Okay, so this is an exercise which we have to traverse a tree. If you don't know how to traverse a tree, I will suggest that you first search on the internet how can you do that, because there are some ways that you can do. And to solve this problem, we will use a way called breadth first search, which is a level by level traversal. And we can apply this approach in a tree or in a graph. We can solve this exercise in some ways, and we will solve here using two ways. The first one will be the iterative way, and the second one will be the recursive approach. For the iterative way, we will need a queue data structure, because for each level, we will need to put the value of the node into a queue, or the node itself into a queue. And in the next iteration, we will check if the left and the right side is not null, and if it's not, we will push again the value into the queue. And by doing this, at the end of the tree, we will have our list of lists. And for the recursive approach, we will not use the queue data structure, because we will handle this by using a level variable, which will be an integer variable. And by controlling this level, we will also use the level variable to access an index in our result variable. Because if the current level in our level variable is equal to the length of the result variable, which is a list of lists, it means that we achieve a level of the tree that is not present yet into this result variable. So in this scenario, we will have to create another list into this result variable and start to populate with the current variable of the node itself. So yes, I think that's a solution for the recursive way. And let's see how this works by writing some code. So let's start by coding the first solution using the queue data structure. We can start by checking if our input is valid. So if root is null, we can just return an empty list. We can also already declare it here. Var result is equals to list of int. And if root is null, we can just return result here. Otherwise, we can also start to declaring our queue. So queue is equals to a new queue of tree node. And also we can already enqueue this root here. Okay, so after that we can start our iteration. So while queue.count is greater than 0, we can iterate through this queue. Okay, we can already return our result here. And now let's do the work. Let me see. So by now we have to know how many nodes exist in the current level, so we can get the count of the queue. So let me see, count nodes in level, which is the queue.count, because we need this information to start another iteration, because we have to get all the nodes that are present in the queue, but just for the current level. So with this information here, we will control our next iteration. So we can do this by a for var I equals to I. It's not I, or it could be I, okay. Could be I and could be 0, because we are going to iterate through, let me see, so while I is less than count nodes in level I++. By doing that, we can start to retrieve all the information that are already in the queue. But we also need to declare a list here, because we need to put lists into our result variable, as the description is asking here in the example. So this is a list, this is a list, but this here also is a list. So let's declare the nodes in level is equals to new list of integer. And here we can just get the current node of this queue. When I get the current node of this queue, I can already put this in the nodes in level. So nodes in level dot add the current node dot vol. And also I can check if the left side and the right side of the current node is not null, because if it's not null, I can put it into the queue for the next iteration. So if current node dot left is not null, I can enqueue the current node dot left. We have to do this also for the right side. And I think that's it for this for loop. And after we get out of this for loop, we have to add the list nodes in level into the result variable. So the nodes in level. And if we do not have any typo here, I think that's the solution using the queue data structure. Let's run the code. Line 27 equals line 16, list cannot be used like a method. So line 16, our result is equals to list of its new list. Line 35, name current does not exist. It's not current, it's current node. So let me see. Line 35, current node, and also here, current node. So many errors. Output is equals to empty. So let's see where we did something wrong here. So equals 0, while I is less than count nodes in level. I++. So Here we add nodes in level, current node dot vol, and after the for loop, we add the nodes in level into the result variable, while count is greater than 0. So let's try again. Okay, let's try to hit submit. That's it for the solution using the Q data structure. So time complexity here, let me see, as we are iterating through all the nodes of this tree, is big O of n, where n is the total number of nodes of this tree. And the memory complexity here, let me see, as we are using the Q data structure, and we are doing this level by level. I'm not 100% sure, but I think that we are gonna use a memory that is equivalent to the biggest level of this tree. Yeah, so I would give a shot for big O of k, where k is the number of nodes in the biggest level, where biggest level is the level that has the most amount of nodes into the stream. Yes, I think it is. I think that's it. And if I'm wrong, please correct me in the comments. And let's try the solution using the recursive approach. So I'm gonna erase this. Okay, so as I said before, the recursive approach here, we will use a level variable, which will be an integer, and this level variable will control the level of the nodes, and we also will use this variable to access our result variable index by index. So let's do this by creating our recursive function here, which will be void and can be called level order. We're gonna use the root node, the level variable, and also the result variable. The result variable is a list of, we can do this list of I list of int, and it will be our result variable. Okay, I think that's it. We can start by, let me see, as this is a recursive approach, we can start by checking the base case. So the base case is if root is null. If root is null, we can just stop the iteration, stop the recursive call. And now we can check the level. So if level is equals to result.count, so here means that we achieve the maximum length, we achieve the end of the result list, and means that we have to create another list into our result variable. So result.add new list of integer. So by doing that, right now we can access this new index and put the current node value into this index. So result of level dot add the root dot vol. Okay, so after that we can go to the recursive case. So the recursive case here, we call the level order. We have a typo in the name of the method, so it's order. And also a typo here, level order, calling root.left, level +1, and result. Have to do this for the right side with the same level +1 and result variable. We also have to call the recursive function here. So let's start by declaring the result variable, which is a list of int. We can now call the recursive function level order result level 0, and first is the root, after is the level 0, and after the result variable. And we can just return result here. So let's check. I think if we do not have any typo here, that's the recursive approach. So let's try to run the code. List like a method. So line 16, it's new. Again, the same error as before. Yeah, so let's try to run the code. And let's try to hit submit. Okay, let's try again. Yeah, so that's it. So for the recursive approach, time complexity is still the same. It's because of n, where n is the number of nodes into this tree. And the memory complexity here, as we are doing a depth first search here, we are going as deepest as possible to the left side first. I think the memory complexity here will be the height of the tree, as we are going as deep as possible. So yes, the memory complexity here is the height of the tree. So that's it, guys. Thanks for watching.